Now, our next speaker is Robert Jacobs, who will talk about Fibonacci multiplication. Please.
Okay, hi, I'm Bobby Jacobs, and I'm going to tell you about this thing I discovered called Fibonacci multiplication. So, as a lot of you know, the Fibonacci numbers, they have a recurrence that F0 is 0, and F1 is 1, and Fn is Fn minus 1 plus Fn minus 2. You basically, you start out with 0 and 1. To get the next number, you just add the last two numbers. And then you get this sequence. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Here's like 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, and so on. And there's a lot of other sequences that are very similar to that. Like there's the Lucas numbers. That's very similar, but it starts out with 2 and 1. So Lucas numbers have the recurrence. L0 is 2, L1 is 1, Ln is Ln minus 1 plus Ln minus 2. So then we get 2 plus 4 is 3, and 1 plus 3 is 4. 3 plus 4 is 7, 4 plus 7 is 11, and so on. So we get 2, 1, 3, 4, 7, 11, 18, 29, 47, 76. Yeah. So we can generalize this by creating Fibonacci-like sequence. Okay, and we're going to let the Fibonacci-like sequences starting with A and B. We're going to call it in parentheses A comma B. Okay. So the Fibonacci-like sequence starting with A and B has the recurrence A, B, 0 is A, B, 1 is B, and A, B, N is A, B, N minus 1 plus A, B, N minus 2. Yeah. So if we start out with A and B, we'll get, so we start with A plus B is A plus B. And then B plus A plus B is A plus 2B. A plus B plus A plus 2B is 2A plus 3B. And A plus 2B plus 2A plus 3B is 3A plus 5B. Yeah. So then we get the sequence A, B, A plus B, A plus 2B, 2A plus 3B, 3A plus 5B, 5A plus 8B, 8B plus 13B, 13A plus 21B, 21A plus 34B, and so on. And you might notice that the coefficients of A and B are Fibonacci numbers. And so, in fact, A, B of n is F n minus 1 A plus Fn B. That's a cool formula. So you might wonder if you can multiply Fibonacci sequences. So the basic idea is like in the sequence A, B, it was just like you take two consecutive Fibonacci numbers and multiply one of them by A and then add the other one times B. And so what we can do is actually take like two sequences A, B, and C, D, and so now we can actually take like a sequence where each term is actually a term of the CD sequence multiplied by A plus the next term of the CD sequence multiplied by B. And it turns out, then we'll let the formula for the Fibonacci multiplication, so it's AB times CD is AD minus AC plus BC and AC plus BD. Yeah. Uh, Because basically we're taking like so the AD minus AC plus BC is basically A times the number D minus C was B times C. So like if you look at the CD sequence, the term before the C and D would be D minus C. So it's like A times that term D minus C plus B times C. And then the next term, AC plus BD is just and this time we're taking the two consecutive terms CD and we're doing A times C plus B times D. So then it's AD minus AC plus BC, comma, AC plus BD. And for example, 2, 1 times 3, 2 is 1, 8. Yeah. So that basically is like the Lucas numbers, that's the 2, 1, and then the 3, 2 sequence. If you multiply it, you'll get the 1, 8 sequence. Okay, so here's a simple theorem about Fibonacci multiplication is that Fibonacci multiplication is commutative. Okay. So basically for any A, B, and CD, AB times CD is CD times AB. So let A, B, and CD be Fibonacci sequences. Then AB times CD is parentheses AD minus AC plus BC, comma AC plus BD, parentheses is parentheses CB minus CA plus DA, comma CA plus BB, parentheses, which is CD times AB. Okay. Therefore, it is commutative. We can also prove that Fibonacci multiplication is associative. So basically, like any A, B, C, D, and X, Y, and we'll have parentheses A, B times C, D, parentheses times X, Y is the same as A, B times parentheses C, D times X, Y, parentheses. So we'll let A, B, C, D, and X, Y be Fibonacci sequences. Then parentheses AB times CD, parentheses times XY is parentheses AD minus AC plus BC, comma AC plus BG, parentheses XY, parentheses is, well, it basically equals all this, so it's basically AD minus AC plus BC times Y minus AD plus AC plus BC is X plus AC plus BD times X, comma, AD minus AC plus BC times X plus AC plus BD times Y, which is ADY minus ACY plus BCY minus ADX plus ACX minus BCX plus ACX plus BDX, comma, ADX.
I think we all believe the formula and you don't have to read it all out.
Oh yeah, so basically it will eventually simplify it. It's the same thing as AB times parentheses CD times XY. Parentheses. So that means Fibonacci multiplication is associative. Okay, so this is interesting. So we're going to define this this similar sequence with like the equal sign with the tilde to basically mean that like the two Fibonacci sequences are similar basically if they're basically just the same sequence at different positions. Like for example, in the Fibonacci sequence 1 1 and then it's 2 3. So that means that 1 1 is similar to 2 3 or it's equivalent to 2 3 basically. And the thing is that if we let AB, CD, WX, YZ be Fibonacci sequences, if AB is equivalent to WX and CD is equivalent to YZ, then AB times CD is equivalent to WX times YZ. So this basically shows that the multiplication is well defined, okay? And so like as AB is equivalent to WX, and WX appears consecutive terms in AB, we can assume AD equals or precedes WX. So if one of them comes first, AB will come first. And similarly, we'll assume CD equals or precedes YZ. So we know that AB times CD is AD minus AC plus BC, AC plus BD. And like so then if we can do it by one term, advance AB by one term. So the next term after AB and AB is A plus B, and the next term after CD is C plus D. So that like if you move the CD term by one term in the Fibonacci sequence, well then AB times D C plus D. That's going to end up equaling AC plus BD, comma, AD plus BC plus BD. And then if we move the B um A plus B times CD. That's going to also equal AC plus BD, comma, AD plus BC plus BD. And the next term after, in the sequence after AD minus AC plus BD, AC plus BD, well, the next term is AD plus BC plus BD. So that's equivalent. It's really the same sequence as AC times BC, just moved ahead by one space. So then like we can use induction by induction. And for any WX such that AB is equivalent to WX and YZ such that CD is equivalent to YZ, AB times CD is equivalent to WX times YZ. So now I defined a new thing called the magic number, and let the magic number of Fibonacci sequence be the absolute value of A squared plus AB minus B squared, and let M of A and B be the magic number of AB. It's basically you take three consecutive terms A, B, and A plus B, and you A time like the product of the two terms on the outside minus the middle one squared. Okay, so A squared plus AB minus B squared. Okay, and it turns out for any three consecutive terms of Fibonacci sequence, A, B, and C, and the magic number, the absolute value of AC minus B squared is always the same. This is a constant for all and every three consecutive terms of a Fibonacci sequence. And so if we let A, B, C, and D be four consecutive terms of Fibonacci sequence, we know that A is C minus B and D is B plus C. So if we take the first three terms, the absolute value of AC minus B squared, well, that's the same thing as the absolute value of C times C minus B squared. It's just absolute value of C squared minus CB minus B squared, which is the absolute value of B squared minus B squared plus BC minus C squared, which is then the absolute value of B times B plus C minus C squared, which is then the absolute value of B D minus C squared. So basically, it's the magic number for the first three numbers, A, B, and C, is the same as the magic number calculating using the last three numbers. So then by induction, the magic number is the same for any three consecutive numbers. So now we're going to define a thing called prime Fibonacci sequences. So a prime Fibonacci sequence is a Fibonacci sequence that's not the product of two other Fibonacci sequences other than the regular Fibonacci sequence. So other than the sequence with 1, 1, 2, 3, and so on. So for example, 3, 2 is prime. And here's all the Fibonacci. These are the single digit prime Fibonacci sequences. So they're prime Fibonacci sequences A, B, with 10 greater than A, greater than B, greater than or equal to 0. It's 2, 0, 2, 1, 3, 0, 3, 1, 3, 2, 4, 1, 4, 3, 5, 1, 5, 2, 5, 3, 5, 4, 6, 1, 6, 5, 7, 0, 7, 2, 7, 3, 7, 4, 7, 5, 8, 1, 8, 3, 8, 5, 8, 7, 9, 1, 9, 4, 9, 5, 9, 8. An interesting thing is that the magic number of a positive integer Fibonacci sequence is prime, then the sequence is prime. So like suppose that m of xy is prime, the magic number. If xy is not prime, well then xy is going to equal ab times cd for some positive integer Fibonacci sequence is ab, cd, other than the canonical Fibonacci sequence, which is the regular one, is 1, 1, 2, 3, and 5, and so on. And let m of AB is m and m of CD is n. It turns out that the regular Fibonacci sequence is the only positive integer Fibonacci sequence with magic number 1. So that means that m and n have to both be 1, since these are some other than the regular Fibonacci sequence. And it turns out that magic numbers actually do multiply. Like, so that m of xy is going to equal m of AB times m of CD, which is mn. So that means m of xy is not prime. That's a contradiction. Therefore, xy is prime. Okay, so we're going to try to prove there's infinitely many prime Fibonacci sequences. And so one way we're going to do this is an interesting theorem. Um, so let A and B be integers and AB be an integer Fibonacci sequence. If AB is not equal to 0, 0, and A, B plus 1 is an offset of the canonical Fibonacci sequence, then 10A, 10B plus 1 is not an offset of the canonical Fibonacci sequence. And you'll see why we're going to use this later. Okay, so basically, so like we're going to show that if we have a certain sequence A, B, and you add 1 to it by adding 1 to B, and if that just turns out to be the regular Fibonacci sequence, then you can just multiply it by 10 and add 1, and you'll guarantee to not get the Fibonacci sequence. So suppose A, B plus 1, and 10A, 10B plus 1 are both offsets of the canonical Fibonacci sequences. So they both are like two consecutive terms of the Fibonacci sequence. And so that the Fibonacci sequence, the magic number is 1. So that means that MAB plus 1 is 1 and M10A, 10B plus 1 is 1. And so then like the magic number, so absolute value of A squared plus A times B plus 1 minus B plus 1 squared is going to equal 1. And the absolute value of 10A squared plus 10a times 10b plus 1 minus 10b plus 1 squared. That's also 1. So that means a squared plus ab plus a minus b squared minus 2b minus 1 is plus or minus 1. And 100a squared plus 100ab plus 10a minus 100b squared minus 20b minus 1 is plus or minus 1. So then we can actually do all these different cases based upon which one, if they're one or negative one, okay? And it turns out, so if you actually take 100 times the first number and then subtract that second number, so it's always gonna, so 100 times a squared plus ab plus a minus b squared minus b 2b minus 1 minus 100a squared plus 100ab plus 10a minus 100b squared minus 20b minus 1. It's going to equal something simple, just 90a minus 180b minus 99. And it's 99 if they're both equal to 1. It's 101 if the first thing is 1 and the second thing is negative 1. It's negative 101 if the first thing is negative 1 and the second thing is 1. And it's negative 99 if they're both negative 1. Then we can actually get rid of the 99 and just say that 90a minus 180b is 198 if they're both 1, or 200 if the first one's 1 and the second is negative 1, and negative 2 if the first one's negative 1 and the second one's 1, and 0 if they're both negative 1. Well, since a and b are integers, 90 has to divide 90a minus 180b. So the only possibility out of those that was divisible by 90 is that 90a minus 180b is 0. So that means a minus 2b is 0. So a is 2b. And so we can now plug in 2b into these equations. And it turns out you're going to end up getting that 5b squared is 0. So that means that b squared is 0, so b is 0. And then a is twice that, so a is 0. So ab is 0, 0. So therefore, if AB is not 0, 0, and A, B plus 1 is an offset of the canonical Fibonacci sequence, then 10A, 10, B plus 1 is not an offset of the canonical Fibonacci sequence. And this is why that's important. It's going to be used for the proof that there's infinitely many prime Fibonacci sequences. And it's basically similar to Euclid's proof that there's infinitely many primes. Because there's just finitely many primes. Fibonacci sequences A1, A2 to AN. We can just multiply them all together and add 0, 1 to get A1 times A2 times all the way to AN plus 0, 1. We'll call that B. And suppose B is divisible by some A in the A1 to AN. Well, without loss of generality, suppose B is divisible by A1. Then B is A1 times C for some integer Fibonacci sequence C. Then A1 times A2 times all the way to AN plus A1 is A1 times C. Then A1 times C minus A2 times all the way to AN is 0, 1. Well, that's impossible because 0, 1 is a unit. It's not divisible by anything else. So that B is not divisible by any of A1 through AN because it leaves a remainder of 0, 1. So B is either a prime or divisible by another prime Fibonacci sequence, or it might be an offset of the canonical Fibonacci sequence. And if B is prime or divisible by another prime Fibonacci sequence, then there has to be some other Fibonacci sequences besides A1 through AN. That's a contradiction. But what if it turns out to just be an offset of the regular Fibonacci sequence? That's where we need that other proof because now we're going to use B2 as 10 times A1 times all through AN and then plus 0, 1. So now by the last theorem, B2 is not divisible by A1 through AN because it leaves a remainder of 0, 1. And it also cannot be an offset of the canonical Fibonacci sequence by the last name. So that means that B2 has to either be a prime or it's divisible by another prime Fibonacci sequence. That's a contradiction. Therefore, there are infinitely many prime Fibonacci sequences. Another interesting thing I found is a thing called the conjugate Fibonacci sequence. The conjugate of AB is A minus B. For example, the conjugate Fibonacci sequence of 3, 1 is 3, 2. And we'll let AB prime be the conjugate Fibonacci sequence of AB. So AB prime is A, comma, A minus B. For example, 3, 1 prime is 3, 2. And a cool thing, like the magic number of the are the same for conjugate. So M of AB is M A minus B. Because AB is absolute value of A squared plus AB minus B squared. And it turns out that M of A minus B is also absolute value of A squared plus AB minus B squared. So therefore, M of AB is A minus B. And an interesting thing is like this is cool because if you take the conjugate Fibonacci sequence and you extend it backwards, you're actually going to get like the same as the original Fibonacci sequence, AB, but just backwards with negative signs. Like, if you did 3, 2, so like 3, 1, 4, 5, 9 is the 3, 1 sequence, and its conjugate is 3, 2, 5, 7, 12. But if you extend it backwards, well, before the 3 it would be -1. And then before that, it's 4. Then before that, it's -5. Then 9. So it's 9, -5, 4, -1, 3, 2, and so on. And it's basically like it's the same as the 3, 1 sequence backwards, alternating negative signs. So that means that AB prime of n is -1 to the n times AB of negative n. And you can do this, show it by induction because AB0 is A, and that's an AB1 is B, and ABN is AB, n minus 1 plus AB, n minus 2. Well, we also know that AB prime of 0 is A, and AB prime of 1 is A minus B, and AB prime of n is AB prime n minus 1 plus AB prime n minus 2. So basically, they both start out with A. So the AB of 0 is the same as just AB prime of 0, and -1 to 0 is 1. So that's the same. And we can do an inductive step, and it turns out that for all n, AB prime of n is -1 to the n times AB of -n. Okay, thanks.
Oh,
That
thank you. Thank you very much, Bobby.
okay.
Do we
Do you
have
have
any
any?
questions for our speaker? If not, we thank you again, and the next talk will be in 7 or 8 minutes.
Okay, thanks. Bye.
So, Augustin Munage, if you can share your slides, that would be great.
Okay. Um, can you see it? Is that okay?
Yes.
Okay, thanks.
Yeah, we'll start in a couple of minutes. So Augustine, I have a question. Was the original Besson-Roth-Ono proof using modular forms? And now the idea is to give more different proofs, maybe more elementary proofs?
Yes, it was. I think it was a theorem of lemma. I'm not sure whether it was modular forms. The modular forms did feature in the paper, but maybe not to. But this particular inequality was proved using a theorem of lemma, I think. Yes, so we tried to prove it combinatorially, and it wasn't so easy, but we managed to do some cut and paste and induction. So
Okay,
it
but,
wasn't it, yeah.
but
Then others now.
maybe I shouldn't ask for what might be the secret of your talk. We'll start in
Yeah.
like 2 minutes.
Okay, all right.